Hi there, welcome to the Large Language Models on Android workshop. My name is Wei, and I'm a developer advocate from the TensorFlow team. If you are here to learn about running a large language model on device, you are in the right place. One of the most exciting machine learning breakthroughs recently is large language models, or LLMs in short. These models can generate text, translate languages, and answer questions in a comprehensive and informative way. LLMs, such as Google's Lambda and Palm, are trained on massive amounts of text data, which allows them to learn the statistical patterns and relationships between words and phrases. This enables them to generate text that is similar to human written text and to translate languages with a high degree of accuracy. LLMs are very large in terms of storage and generally consume a lot of computing power to run, which means they are usually deployed on the cloud and are quite challenging for on-device machine learning, ODML, due to the limited computational power on mobile devices. But it is possible to run LLMs of smaller scale, for example, the OpenAI GPT-2 model on a modern Android device and still achieve impressive results. So in this workshop, we will learn how to build an LLM-powered app by using Keras NLP to load a pre-trained GPT-2 model, fine-tune it, optimize it, convert it with TensorFlow Lite, and finally deploy it on Android. This whole process involves multiple steps and is a complete end-to-end tutorial that goes from modeling all the way to mobile deployment. We're going to assume you have intermediate knowledge of Keras and TensorFlow Lite. If you are ready, let's dive right in. Okay, the first thing to do is to open up the code lab that comes with the workshop. You can find the code lab on colabs.developers.google.com. So this is the code lab we will work through, and there are a few prerequisites. As I mentioned before, you should be pretty familiar with Keras API, and you also need to have some good understanding of TensorFlow Lite. And you also need to know the basics of Android development. And in terms of computer setup, you need to have network access to Colab. You need to set up your Android Studio. And if you're going to use an Android device to run the app, then make sure you use a modern Android device with more than 4 GB RAM. If you want to use Android emulator, which will also work, but just make sure you set up the emulator to have more than 4 GB memory. So with that set up, now let's move on to the first step, which is to download the TensorFlow examples repository by going to this link. You can download the entire repository through a single zip file, and after the file is downloaded, unpack the file, and then you will have a examples root folder. The next step is to import the Android code into Android Studio. So go ahead and open up Android Studio and import this folder, examples Lite /examples generative AI folder. So I have my Android Studio open, and go ahead and run the app. So Android Studio will spend a few seconds to download all the dependencies, and then it will run the app. In my case, I'm using the Android emulator. So the app UI is pretty straightforward. This app is called autocomplete. Basically, you can type a number of words in this text box, and then you can ask a large language model to generate additional text for you. So in this case, let's type a simple prompt. I'm enjoying oh, it's not working. Let's try it again. Okay, so it says the autocomplete .tflight model is missing. So we don't really have the TensorFlow model yet. That's why the app is not working. But don't worry about it. We will get to the model part real soon. Okay, so the next step is to prepare the LLM for on-device deployment. Go ahead and open up the Colab interface. And I have my Colab open right here. In this Colab, you will learn to use Keras NLP to load a pre-trained large language model, the GPT-2 model originally invented by OpenAI, fine-tune it to a specific text style, optimize it, and convert it to TensorFlow Lite so that it can be deployed in the Android app, which will automatically generate text in a certain writing style based on user prompt, which is also known as prompt. Note that GPT-2 is used here only to demonstrate the end-to-end process. The techniques and tooling introduced in this Colab are potentially transferable to other generative language models such as Google T5. The first thing is to set up your GPU. Go ahead and change the runtime type to GPU accelerator. So I have my Colab Pro subscription, so I can choose a faster GPU. In your case, T4 GPU should work. Go ahead and connect to the runtime. Let's first install a few libraries and get our imports out of the way. Go ahead and run these two cells. While that is going, let's talk about large language models. Large language models are a type of machine learning models that are trained on a large corpus of text data to generate outputs for various NLP tasks, such as text generation, question answering, and machine translation. LLMs are typically based on deep learning neural networks, such as the transformer architecture invented by Google researchers in 2017, and are trained on massive amounts of text data, often involving billions of words or tokens. These models, such as Google Lambda and Parm, are trained with a large dataset from various data sources, which allows them to generate output for many tasks. LLMs are large not only because of sheer size, but also the vast volumes of data on which they are trained. But at the very core, they're just language models that can predict the next word in a sentence. Language models do this by analyzing the words that have already been used in the sentence and then using that information to calculate the probability of each possible word. This way, LLMs can generate coherent text based on user prompts. For more theoretical discussion on language models, you can refer to this fantastic Stanford LLM course. One of the challenges with LLMs is that they're computationally very expensive to run. For example, generating text with an LLM can take several seconds or even minutes on GPUs. This is particularly challenging for mobile devices where there are very limited computing power and storage space. But LLMs of smaller scale, for example, the GPT-2 model, are more manageable, and you can run them fully on device and still get very impressive results. Now let's talk about Keras NLP. Large language models are complex to build and expensive to train from scratch. Luckily, there are pre-trained LLMs available for use right away. One toolkit that offers state-of-the-art pre-trained models for free is Keras NLP. Keras NLP is a natural language processing library that supports users through their entire development cycle. The workflows are built from modular components that have state-of-the-art preset weights and architectures. You can use them right out of the box, or you can customize them if you want more control. Keras NLP has a special emphasis in in-graph computation for all workflows so that you can expect easy productionization using the TensorFlow ecosystem. For example, deployment to mobile devices with TensorFlow Lite. Keras NLP is a great choice for anyone who wants to build NLP models with Keras. We'll go through the high-level APIs in a minute, but I should emphasize that Keras NLP has a variety of pre-trained models and modules, and it's super easy to use. If you're new to NLP, Keras NLP is a great place to start with. There's also a separate technical talk, Applied Machine Learning with Keras CV and Keras NLP, by my colleague Jonathan Bischoff. Make sure to check that one out as well. Keras NLP provides a number of pre-trained models such as Google BERT and GPT-2 models. You can see the entire list of models available in the Keras NLP repository. It's actually super easy to load the GPT-2 model. Go ahead and run this cell. We will talk about the tokenizer and the preprocessor in a little bit. The key here is we're using the GPT-2 causal LLM model by calling from preset function to load a pre-trained GPT-2 model. Keras NLP will just go ahead and download all the necessary files for us. Once the model is downloaded, you can use it to generate some sample text right away. Go ahead and run this cell. So in this cell, what we are doing here is we're passing in a prompt, which is a string of words, and we're calling this generate function using the prompt, and we're also specifying a max length of 200 tokens. The GPT-2 model will then generate additional text based on my prompt. So in this case, it will take a few seconds to run. Okay. So now we get the GPT-2 model output here. My trip to Yosemite was one of the best experiences of my life. I was so close to the top. I had a beautiful view of the mountains. So this looks pretty good to me. It's pretty coherent text and definitely human readable. Now let's try another one. This time we're using a different prompt. That Italian restaurant is. Okay, so the output we are getting is the Italian restaurant is a place that is not only a restaurant, but also a place that you have to be there for. So this looks like a pretty good restaurant review. One thing I should point out is that notice in the first round, it took roughly 31 seconds. But in the second round, it took less than 2 seconds. Why is that? Why is it so much faster in the second round? This happens because the computational graph is compiled in the first round, cached, and reused in the second round. That's why the second round is so much faster. Keras NLP is being smart here. So as you can see in the sample text we have generated, the quality looks okay, but you can improve it with fine-tuning. Before we talk about fine-tuning, I figured it would be much helpful for you to understand all these sub-modules inside the GPT-2 model within the framework of Keras NLP. So in this section, we're going to dissect the GPT-2 model and then go through each sub-modules inside it. You can, of course, check out the entire GPT-2 model implementation on GitHub in this link, but conceptually, the GPT-2 causal language model can be broken down into several modules inside Keras NLP, all of which have a from preset function that loads a pre-trained model. As you can see in this diagram, at the very top, we have the GPT-2 causal LLM model, and inside that model, we have the preprocessor and the tokenizer. We also have a backbone module. We'll go through each one of them now. First, the tokenizer. The tokenizer converts your text into token IDs. There are different kinds of tokenizers. GPT-2 model uses the byte pair encoding tokenizer. You can refer to this Stanford lecture material for further discussion on BPE tokenization. In this case, I'm using this prompt. Today is a beautiful day, and the tokenizer gives us the token IDs for these 5 words. Next, the preprocessor. The preprocessor does additional processing. For example, padding the tensor of token IDs to a specified length after tokenization is finished. Go ahead and run this cell. We're using the same prompt. Today is a beautiful day. And let's see how the preprocessor does. We're going to use the tf.data API to map the preprocessor against a sample dataset. And as you can see here, we're getting the same token IDs as before at the very beginning of the tensor of tokens. But after that, we're getting a bunch of 50256. What is this number? So it turns out 50256 is the end of sentence token for the GPT-2 model and is used to pad the tensor to the length as we specified when the preprocessor was created. If we scroll up back to the very beginning of this notebook, we can see here, when we created the preprocessor, we specified the sequence length as 256. That's why the end of sentence token was added and padded to the tensor of tokens. One thing you may have noticed is that the shape of the tensor is actually 255 instead of 256 as we specified in the sequence length. Why is that? Well, this is because the label for language models is always the next word. So intuitively, the input tensor is shifted towards the end by 1 as labels. Thus, the element at the very end, the 256 element, is truncated. Now, moving on to the next module, the backbone module. The backbone builds up the neural network and is where real actions happen. So due to the time limit of this workshop, it's impossible to cover the entire GPT-2 architecture in this workshop. You can, of course, check out the full backbone implementation in this link. At a high level, GPT-2 model is a decoder-only model, and its core is a stack of transformer blocks. As I mentioned before, the transformer architecture was invented by several Google researchers in the 2017 paper, Attention is All You Need, which by now is very famous in the NLP domain. The transformer architecture is now the foundational building blocks for many NLP tasks. It is superior to recurrent and convolutional neural networks because it can handle long-range dependencies and allows for significantly more parallelization. You can follow a full transformer implementation tutorial at tensorflow.org to learn about all the implementation details. But at the very core, the transformer architecture relies on something called scaled dot product attention. So I have borrowed a diagram here from the original transformer paper. So if this is the first time you hear about attention, basically attention is a mechanism that enables a neural network to selectively focus on certain parts of the input data. And scaled dot product attention is a specific type of attention, which mathematically is defined in this equation. So in this equation, we have a Q, which is the query matrix, and a key, which is a key matrix, and a V, the value matrix. And the dk is the dimension of the key matrix. It might be a little hard to understand what's going on here if this is the first time you see this diagram and this equation. But let me try to help you understand this by using an analogy that I find intuitive. So let's say you're asked a question on a subject you're not familiar with at all. For example, quantum chemistry. So I'm totally making that up. Let's say the question is a query and you have no idea how to answer it. What you can do is to go to a local library and read books on that subject. There are many books in the quantum chemistry section, so you don't really have the time to read all of them in detail. What you can do is to match the question against the book title first. The more compatible or similar the query is to a book title, the more relevant that book's content may be to the query question, which means you want to spend more time or more attention on that book. So in this case, we have the book title as the keys and the book content as the values. We use the compatibility or affinity of the query and the keys to compute the attention score, which is what's happening in this entire block of calculations. Then based on the attention scores, we take the weighted average of the values, which are the book's contents, and then we do a dot product, which is in this matmul, and then we use the output to synthesize an answer to the original query question. Obviously, this is a very simplified analogy and does not talk about the sequence of queries, masking, self-attention, scaling down of the values, cross-attention, and a lot of other details, but you get the main idea. In practice, you will perform the attention function in parallel and then concatenate the output, as you can see here. So in this case, it becomes multi-head attention, MHA in short. You can check out how the MHA is implemented in Keras NLP in this link. There's another important element in the transformer architecture I want to mention, which is the positional embedding. Since there's no recurrency or convolution in the transformer architecture, positional embedding is used to inject token position information into the word embedding. So in the interest of time, I encourage you to learn about positional embedding in the original paper. So now we have talked about all the submodules. We can put them together, and finally we have the GPT-2 causal LLM model. The GPT-2 causal LLM model has a predict function that outputs the next word prediction logics, which can be turned into probabilities through a softmax layer. So go ahead and run this cell, and you will get a bunch of numbers, which are the logics. Of course, there's also the generate function that generates the prediction text output by repeatedly sampling for the next word from the predicted probability, given the user prompt, of course. You have seen how to use this function at the very beginning of this collab. By the way, you may have noticed the word causal in the model name. So transformers are autoregressive models that generate text one token at a time and feed that output back into the input. To make this efficient, these models ensure that the output for each sequence element only depends on the previous sequence elements. These models are causal. There's another kind of language models called masked language models. For example, Google's BERT model is one such type of masked language model. These models, what they do is they will randomly mask out a certain number of words in the input sequence and then use a neural network to predict those masked out words. That's the name, masked language models. Okay, so now you have a much better understanding of the GPT-2 model from Keras NLP. You can take one step further to fine-tune the model so that it generates text in a specific style, for example, CNN's writing style. We're going to do a fine-tuning using CNN's Daily Mail dataset. This step will take more than 30 minutes to run, so it's optional for the workshop. If you do want to do the fine-tuning using the CNN dataset, go ahead and run this cell. What this cell does is it uses TensorFlow Datasets API to download the CNN Daily Mail datasets. Okay, so the download has finished. Now go ahead and run this cell, and we can take a look at a training example. So there are two features in this dataset, the article feature and the highlights feature. So article is really the raw text of news article. As you can see here, this is basically CNN's news article, and this is the highlights, the main points of the article, which can be used as a summary label if you want to do a summarization task. In this case, we're performing next word prediction in a language model, so we only need the article feature. To further prepare our training data, we're going to use a NLP package, NLTK. NLTK helps us download a sentence tokenizer punct, which divides text into a list of sentences. Next step is to define a simple helper function to merge shorter sentences into longer ones until they reach a predefined max length. Now we can go ahead and process our training dataset. Note in this loop, what we're doing here is, first, we split articles into sentences by using the punct tokenizer, and then we merge individual sentences into longer context. And then lastly, we merge the context into a collection. The next step is to create a TensorFlow dataset and run preprocessing on it. Here, we're using tf.data API to map the GPT-2 preprocessor against the training dataset. In the interest of time, here we're only taking the first 100 training examples from the dataset. Now you can fine-tune the model using the familiar Keras fit function. Note here, we're turning off preprocessing inside the GPT-2 language model by setting this flag to false. The fine-tuning takes quite a bit of GPU memory and a long time if we were to train it all the way to a fully trained state. Here, we're just training one epoch as a demonstration of how this goes. The rest of the code should look very familiar to you in this cell. For example, the compile function and the fix function. So this step will again take a few minutes, and it also depends on your GPU setup. So let's give it a little patience. Okay, the fine-tuning step is finished. Now you can go ahead and run the cell to generate text using the same generate function. This time, the text will be closer to CNN's writing style. Note that we are here using a different prompt, breaking news, the river. Let's see what we get out of the fine-tuned model. Breaking news, the river was still running in the direction of the river, and the storm was still moving in the east direction at the time of the storm. Looks pretty good to me. Definitely looks like a news article. You can save the fine-tuned weights for future usage. And you can, of course, fine-tune the model to any writing style as you want, as long as you can provide the training dataset. This is left to you as an exercise after this workshop. Since it takes a long time to fine-tune the GPT-2 model to completion, you can download a GPT-2 model fine-tuned on the CNN Daily Mail dataset directly from Keras NLP. Go ahead and run this cell, and Keras NLP will go ahead and perform the download. And at the end of the download, we're using the same generate function to generate some text based on the same prompt as before. Breaking news, the river. Okay, so this time we're getting breaking news, the river that is the world's largest and the biggest. The US government says there's no way to get there safely. But a new study by IMB. Okay, so this is definitely more like CNN's news article. Now the model can generate text of our intended style, but this runs on a powerful GPU sitting in the cloud. How can we leverage it on a mobile device? One solution is to, of course, build a backend service using Keras NLP and then send the requests from mobile devices to the endpoint. But a better way is to just run the model purely on device using on-device machine learning, ODML. This is where TensorFlow Lite comes into the picture. TensorFlow Lite is a mobile library for deploying models on mobile microcontrollers and other edge devices. You can learn more about TensorFlow Lite from its homepage. But here's a conceptual architecture for TensorFlow Lite. There's a converter and there's an interpreter. On the hood of the interpreter, there are highly optimized off-kernel implementations that are designed and implemented for ARM Neon instruction sets. You can also leverage hardware accelerators like GPU or even DSPs to make your model run even faster. The high-level developer workflow for using TensorFlow Lite is first, convert a TensorFlow model to the more compact TensorFlow Lite format using the TensorFlow Lite converter. And then use the TensorFlow Lite interpreter, which is highly optimized for mobile devices, to run the converting model. During the conversion process, you can leverage several techniques such as quantization to further optimize the model and accelerate inference. Now, we should go ahead and convert the generate function. The generate function from the GPT-2 causal LLM model is the actual function that does the magic and generates text for us. Go ahead and run this cell. What this cell does is wrap the generate function into a TensorFlow concrete function. Now define a helper function to run inference with a given input and a TF-Lite model. Note that here, TensorFlow text ops are registered as custom ops so that the interpreter can run smoothly, as you can see in this line. Now you can convert the model. Note that the converter needs to pull in select TensorFlow operators and enable custom ops due to the model complexity. Specifically, the TensorFlow text operators are used under the hood inside the GPT-2 model in, for example, the tokenizer. At the end of the conversion, we run a sample inference using the simple prompt. I'm enjoying a good time, and I'll do whatever I can for the people that need me. Looks pretty good. Now we can save the TF-Lite model and take a look at the size. Right now, the model is roughly 500 megabytes and can already be run in an Android app if you want to. But you can do better. TensorFlow Lite has implemented an optimization technique called quantization to shrink down model size and accelerate model inference. Quantization is a process of mapping an input of continuous values to a discrete set. So in the machine learning domain, it is done by converting 32-bit floating numbers in the model weights to more efficient 8-bit integers, which leads to a 4x reduction in model size and more efficient execution on modern hardwares. So here's a simple diagram that shows how we actually map the floating numbers into 8-bit integers in the range of -127 to +127. There are several different kinds of or flavors of quantizations implemented by TensorFlow Lite. There's post-training quantization, and there's also quantization-aware training. You can visit the TensorFlow Model Optimization page and TensorFlow Model Optimization Toolkit page to learn more about quantization. In this workshop, you will use the simplest one, post-training dynamic range quantization, by setting the converter optimization flag, as in this line. So we're going to set the flag to tf.lite.optimize.default. The rest of the other conversion code is exactly the same as before. And we're again running the same inference using the same prompt as a quick test. Okay, so the conversion for the quantized model is finished, and let's take a look at the generated text. I'm enjoying a good night's sleep, and I can't wait to go back to the beach. So this is still pretty good quality. Now save the quantized TF-Lite model, and let's compare the size of the quantized and non-quantized model. As you can see here, we basically cut down the size by roughly 300 megabytes, which is massive for mobile app distribution. Now, rename the quantized model to autocomplete.tflite, which is what will be used in the Android app. After that, you can go to this Files panel on the left and download the autocomplete TF-Lite file. It will take a few minutes to download, and in the meanwhile, while we're waiting for that, I want to introduce you to a new and very exciting new feature we're developing. The feature is called Visual Blocks for machine learning. Visual Blocks for ML is a new JavaScript framework from Google for rapid prototyping and experimentation for various machine learning tasks. You can connect machine learning blocks in endless configurations to build highly interactive experience in minutes. Off-the-shelf blocks include models, user inputs, processors, and visualizations. So here's an example UI of Visual Blocks. As you can see here, on the bottom left corner, we have a node library, which is a collection of different nodes. These nodes can be server-based models that you can call via API calls. They could be on-device machine learning models, for example, TF-Lite model or TFJS model. They could be pre-processing or post-processing nodes, and they could also be visualization nodes. You can actually drag those nodes into this editor portion of the UI and make them as a pipeline of nodes. And in this section of the UI, you can run those nodes as a pipeline, and it will be orchestrated and executed in this runner section. One nice thing about Visual Blocks is that it has a Colab integration that allows you to use any Python function as a custom node. So in this section, we will learn how to experiment with Visual Blocks using the TF-Lite model you have just produced. The first step is to read the TF-Lite model back in. And then next, we're going to define a small helper function to run inference. This code is pretty much the same as before, except at the very end, we're returning a dictionary. And this function will become a node in the pipeline, as you will see in a minute. The next step is to import Visual Blocks. So don't worry about all this code. We're working on packaging everything up into a simple pip wheel package. By the time you're watching this video, you should be able to just do a simple pip install and everything will be set up for you. Now go ahead and run these two cells. What they do is they will start the Visual Blocks server and display the UI. It takes a few minutes for the server to be created and started up, and let's give it a little time. Okay, so the UI is loaded. As I mentioned, so this is the node library. For example, let's drag this input text in here, and then let's pick a model. You can directly connect them. So this is probably the simplest pipeline in the use case of visual blocks, but it demonstrates the idea of visual programming without actually writing much code. So we're going to import a pipeline that we have prepared for this workshop. So we're going to import this pipeline, and then we will recreate the Visual Blocks server, which again will take a few seconds. Now let's display the UI again. Okay, so this is our new pipeline, and as you can see here, we have 6 nodes, and what this pipeline does is it will allow the user to select a category of news, and then it will automatically fetch news from a news aggregator website, and then we can select a sentence and then feed that sentence into our GPT-2 model. And let's run that. So this is the custom node that has our defined helper function, and it's basically just running the GPT model using this sentence as the prompt. Okay, so now it has generated text based on the sentence we selected. Look inside my small kitchen, and you can see that I'm very proud of myself and my family. I think I'm very proud of the whole world. This looks very good. So as you can see, this kind of a visual programming lets you rapidly prototype with your ideas without writing much code. Okay, so we have our TensorFlow model ready and downloaded. Now let me switch back to my Android Studio. So I have my TensorFlow file here, and let me drag that into the assets folder. And okay, so it's just finished downloading right in time. So after we add that file to Android Studio, let's rerun the app. Again, Android Studio will try to build the app and launch the app. Now this time, let's use the same simple prompt. I'm enjoying something, and let's run the large language model. One thing I should point out is that my internet connection on the Android simulator is turned off. So everything runs on the device and no data ever leaves the emulator. As you can see, it generates a number of words in orange as a suggestion, and you can accept or reject the suggestion. Let's accept that. And you can generate some more. See, you can keep going, and the model will spit out more text for you. And you can literally use this as a writing assistant. Okay, let's generate one more. Okay, so that's our Android app. Of course, I'm running this in my Android emulator. Feel free to run it on your physical phone. It will work. I can assure you that. Okay, so now let's switch back to the code lab, and we have already completed our Android app. And I want to make one really important note about responsible AI. So in this workshop, We're using the GPT-2 model as an example language model. But as noted in the original OpenAI GPT-2 announcement, there are notable caveats and limitations with the GPT-2 model. In fact, LLMs today generally have some well-known and very common challenges, such as hallucinations, fairness, and bias issues. This is because these models are trained on real-world data, which makes them reflect real-world issues. So this collab, and by extension this workshop, is created only to demonstrate how to create an app powered by LLMs with TensorFlow tooling. The model produced in this collab is for educational purposes only and not intended for production usage at all. So do not deploy the model into your production app. LLM production usage requires thoughtful selection of training datasets and comprehensive safety mitigations. To learn more about responsible AI in the context of large language models, make sure to watch the Safe and Responsible Development with Generative Language Models technical session at Google I/O 2023. You can also check out the Responsible AI Toolkits at tensorflow.org. Congratulations! You have built an amazing app that can generate text based on what you type. Everything runs on device and no data ever leaves your phone. This is very remarkable if you think about it. Now, as a retrospective, let's summarize how we achieved this. We used Keras NLP to load a pre-trained GPT-2 model, fine-tuned it with a custom dataset, optimized it with quantization, converted it with TensorFlow Lite, and finally run it on Android. That's the full development cycle. Even though GPT-2 may not necessarily be the model you want to use in your actual use case, the techniques you have learned in this workshop are transferable to other LLMs. So we can't wait to see what we will build with our tooling. With that, thank you very much for watching this workshop and happy coding.